In this session, we are going to derive the Jacobian matrix for RPY Wrist. So the Jacobian matrix, the columns of the Jacobian matrix correspond to the joints. So if you have n joints, then you will have n columns in the Jacobian matrix. So here, the Jacobian, it has each column, it will have two components. That is, it will have the linear velocity component as well as the angular velocity component. So you will determine the linear velocity component by using Zi, the cross product of Zi minus 1 and On minus Oi minus 1 if it is a revolute joint, and simply Zi minus 1 if it is a prismatic joint. And the angular Jacobian, it is Zi minus 1 if it is revolute joint, and it is 0 for prismatic joint. So we are going to derive the Jacobian for RPY wrist. So as you know, the wrist, it has a spherical joint. So the rotation by the spherical joint can be expressed as three intersecting revolute joints. That is how we have done. We did it in while deriving the forward kinematic model. That is, we derived the DH parameters just by assuming the frames intersecting three intersecting frames. That is, we considered three intersecting revolute joints, and we have derived the DH parameters, and from which we have got the transformation matrices also, right? So we'll just continue from there. So the transformation matrices, that is T1 to 0, then 2 to 1, and 3 to 2. So the three transformation matrices that we have got for the RPY wrist earlier. Now we will directly use that here. So here this is the forward kinematic model, that is T3 to 0, right? So that we have got it by multiplying the three transformation matrices. In order to derive the Jacobian, we want T1 to 0, then T2 to 0, and also T3 to 0. So T1 to 0 is there, and T3 to 0 is also there. So but we have to get T2 to 0. So how will you get it? Simply by multiplying the transformation matrices T1 to 0 and T2 to 1. So multiplying these two matrices, you will be getting T2 to 0. So that is shown here. So you want to get T2 to 0. So just multiplying the two matrices, you will be getting this transformation matrix, right? So now you have assumed it as three intersecting revolute joints. So you have three columns in your Jacobian, that is J1, J2, J3. Three columns you have the complete Jacobian have three columns. So one by one we will just derive. That's first you will take the J1. For J1, the formula is, so we have to use all revolute joint. Okay, so you have the linear Jacobian and the angular Jacobian. For the revolute joint we have to use. So J1 is equal to the cross product of Z0 and O3 minus O0 and Z0 here, right? So as I have discussed earlier examples also, Z0 is always 0, 0, 1 and O0 is 0, 0, 0, right? And O3, what is O3 here? So that we will be getting the positional vector of the transformation matrix 3, T3 to 0, right? From that you will get O3, right? So just this is the J1 matrix. So just you have to take the cross product. In this case, the cross product is all 0 here. So we will be getting J1 as 0, 0, 0 and 0, 0, 1. Right? Then you have to get the same way you have to get for J2. J2 it is Z1, cross product of Z1 and O3 minus O1. And the angular Jacobian, it is simply Z1, right? So from the transformation matrix T1 to 0, you will be getting the Z1 values, and the same way T1 to 0 positional vector and T3 to 0 positional vector you have to take, right? So again, the positional vectors of all the three transformation matrices will be 0 in case of RPY wrist. So you will be always getting this term to be 0, and Z1 from the transformation matrix you have got, and hence by substituting you will get J2. The same way you also should get J3. So combining the three columns, that is J1, J2, J3, you get the final or the overall Jacobian matrix of the RPY wrist to be this. So as you see here, the linear Jacobian components, all the components are 0 here. Okay, and you have only the angular Jacobian components. Okay.